Alright, so we're going to look at kinematics in 2 dimensions, right? We spent a lot of time looking at it in 1 dimension and deriving the equations for the kinematic equations. Now we're going to look at 2 dimensions, and that makes it much more realistic to us because we see more than 1 dimension, right? It's kind of hard picturing something traveling all along a straight line, but it's actually easier to see something traveling like this. So I'm just going to draw a ball, right? And it's just going to be launched, right? This lands here, for example. Right? We can imagine this much better and track its motion. But at the same time, it also gets a little bit more complex because we are adding 2 components to this. The way I like to think of this is called projectile motion, right? Where we throw a projectile in the air and it does its thingy going up and down, and also does its thing going right? So the way it is broken into 2 parts. It is broken into a uniform velocity, or constant velocity if you want to think of it like that, and uniform acceleration. So remember, I actually derived these two types of uniform velocity equations and then the uniform acceleration equations in previous videos. So this is where they both come together, and this is where we actually see it. So I'm going to write the uniform velocity equations in blue. So remember, the position is actually just a measure of this, and then also the velocity is a constant, so no matter what, the velocity will always equal the initial velocity, right? And then uniform acceleration. We did that a lot in the past, I guess, 3 videos now. So here they are, v naught plus at, and then we have position or displacement equals the initial velocity times time plus 1/2 at squared. We also have v squared equals v naught squared plus 2a delta x, and then we have the average velocity is equal to the averages of the velocity, which is that, right? 2 parts, uniform velocity and uniform acceleration, and maybe you see where I'm trying to go at this. This is all about the x, or horizontal. This is all about the y, or vertical, right? So it's kind of broken down into 2 parts. In fact, let me just change all these to y's, because it'd probably be better to represent them as y since we're talking about vertical, right? And there's a y here. So in fact, projectile motion is just into 2 parts. We have a free fall, right? Free fall. And then we have the horizontal, right? We did a lot of free fall last time, and now we are just adding in this horizontal component. So just think of projectile motion as free falling with a horizontal component that's defined by these 2 equations. Notice that there is no acceleration, so a is equal to 0. That's also just another key thing. And then let's scroll down a little bit. The thing is that even though they're broken down into 2 parts and they're kind of independent from each other, so let me just write that, independent from each other, right? Even though they are independent of each other, meaning that the vertical stuff won't really affect it won't at all actually. It won't at all affect the horizontal, and then same with the horizontal. It will never affect the vertical. Even though they're independent from each other, they are linked by 1 variable, 1 kinematic variable, and that is time, right? We arrived at the destination, horizontal and vertical, at the same time, no matter what. So if I were to drop a ball, we do our uniform velocity equations here, horizontal maybe, and we find the time, for example. We can use that exact same time to help us use with the uniform acceleration. So that's always really helpful to know. So we're going to do like some review. So I have this right here. I drew this. What we want to do is review vectors, and when we throw something, we usually throw it off we drew it off like with an angle, so you want to actually find this. because we can't express this as a motion in the diagonal direction. I mean, it's better to represent it as a horizontal, which we can use with the uniform velocity equations, and then the vertical, which you can use with the vertical motion. So just some review. Remember that the sine of this angle is Vy, or opposite, and then over hypotenuse, which is V. And then we want to solve for Vy, right? So I solve for Vy, and then Vx, right? Vx is just the adjacent over hypotenuse, Vx over V, and then multiply V at the bottom to get rid of it to solve for Vx. I guess what a lot of people get confused is that just because x is with cosine does not mean it's always going to be in that case. In cases like these, the way I like to think about it is, what is this angle? If it's adjacent to it, that's the cosine version. If it's the opposite of it, that's the sine version, right? We can have a thing here, right here. Maybe this is the angle, and it's pointing this way. They give us this angle instead of this angle. A lot of people would say this is the V sine theta, just because that it's kind of like the vertical component, but it's not in this case. It's actually the cosine, and this is the V sine, right? Because this is opposite. So that's the way I like to think of it. Whatever this angle is compared to these sides, right? This is opposite, so it's sine. This is adjacent, so it's cosine, right? So that's just something a lot of people can get confused on sometimes. So we're actually going to look at an example right now. So okay, this problem is more of a conceptual example than just plugging in numbers and getting an answer, like a numerical answer. This one will just be like an equation that describes the motion. So that's how we're going to think about it. So the first part tells us to describe the position of the particle launched at an initial velocity at 5 meters per second at an angle of 45 degrees above the horizontal. Then we should describe the velocity and acceleration kind of the same way. So let's look at that. So I'm going to just draw a picture, because pictures really help, especially in physics. We have this, and we have this angle of 45, and it probably goes something like this, right? We want to describe the position in terms of a horizontal and a vertical thing, right? So I'm going to break it down into components. Since this is the angle, the adjacent, and let's say this is V, right? We know V is 5 meters per second. So this is 5 cosine of 45, since it's adjacent to the angle. This is 5 sine of 45. And if you really want to evaluate this, this is 5 root 2 over 2. This is also 5 root 2 over 2 because of what the sine and cosine of 45 degrees are. They're the same. Now we want to describe them using a position. So position function, I'm going to do this as the x version and this as the y version. So remember that the position, using the horizontal, let me scroll up here. Using the uniform velocity equation, the position is described as its initial position time plus velocity times time, right? So that's exactly how we're going to describe it. We're going to say the particle starts at 0 here, so 0, and then we're going to add vt, or the velocity that is also in that direction, times time, which is equal to 5 square root 2 over 2. Let me just write it like this, t, and that's how we can describe its position along the x. Let's describe it along the y, right? The y is a little bit more confusing because it's uniform acceleration. I think the second equation will work the best, since y is basically the function right here. So y, so this is v naught t plus half a t squared. This one might take a little bit longer to think about. So the initial velocity in the y component is 5 root 2 over 2 t plus 1/2 at squared. In this case, a is still negative g. I'm going to approximate it to negative 10, so it would be negative 5 t squared. And that's exactly what we just did. We described the position of the particle launched at an initial velocity of 5 meters at an angle of 45 degrees above the horizontal. So if I were to give you any time, t, I can find the position just using this function right here. Same with the y, I can just describe it using this function here. Now let's describe the velocity and acceleration. this is actually pretty simple because all we have to do is just take the derivative of each. So the v component is the derivative of x with respect to time, which is just 5 root 2 over 2. And we can see this is a constant, right? So that's constant velocity. Just further proves that it's constant velocity. And then let's look at the y component of t, which is the derivative of y with respect to t. Let's take the derivative of this expression right here. It is 5 root 2 over 2 minus 10t. And these two equations describe the velocity of this projectile being launched at this specific condition. And finally, we want the acceleration, right? The acceleration in the x direction, if we take the derivative of velocity in the x direction with respect to time, we would get 0, right? This just shows that there's no acceleration in the horizontal component. So that makes sense because we're talking about constant velocity. So acceleration never changes, or it never changes the velocity. And then similarly, a y is the derivative of the whole vertical component of velocity with respect to time, which in this case right here, this is the first term's a constant, so we're just left with -10, which is what we approximated to be -g, right? So we prove that the y component of velocity is just gravity, and that's what we base it on Earth, right? Gravity. Acceleration is constant, it is simply -g. So if you want to look at this example, basically what I did was I used one of the equations that described the positions. This one's the uniform velocity, uv, and this one uniform acceleration. And then I just found the derivatives. And this problem wasn't that bad because calculus is there to help us. Right, with the second part, it basically using the same example. How far has the particle traveled when the projectile reaches its peak? So remember, at a peak, at the highest point, the velocity in the y component is equal to 0. So we can actually take this equation here and set it equal to 0 to solve for t. Okay, and then we just simply solve for t, right? So 10t is equal to 5 over 2 square root 2, divide 10 by both sides. We get 5 root 2 over 20 equals t, which is also equal to root 2 over 4. So that's what time is equal to. And then now you just basically remember that time is the thing that links the horizontal parts and the vertical parts together. So we just basically plug this time into the position function, which we found to be 5 square root 2 over 2t. This is our thing. This is our position function. Let me just be clear by moving this here. This is our position function, and we just plug in the value that we know. So it's equal to, so if we put x root 2 over 4, we get 5 root 2 over 2 times root 2 over 4. In other words, 5 times 2 divided by 8, which is 10 over 8, which is 1.25 meters, and that's the answer. So see how easy it is just to relate vertical and horizontal together through time, and we can find a vertical component easily. It's not too difficult, but just remember we might have to do something like this. This might be really helpful for us. And also just makes us remember only two specific equations most of the time, which is the position right here and the velocity one, the second one right here. Right, to find position, it's not too bad. So that's it for, I guess, this unit. I'm probably going to do a bunch of practice problems in a video related to this unit. So that's it for learning about this unit, but now we're just going to put it in practice. So that's it for this one.